This is a question. The propagation of a nuclear explosion shock wave depends on E, capital letter E stands for the energy, and then R, so that is the distance, then rho, that is the mass density of the fluid involved, so that is air, and then T is the time. So energy, the distance of propagation, mass density of the fluid medium, and the time taken, T. So only 4 variables. So therefore, this particular problem related to explosion shock wave, so can be modeled as function of, see this, function of energy E, then distance of propagation R, mass density rho, and time taken T. Function of all this is equal to 0. Or if you want to talk about distance of propagation R, then R will be a function of the other 3 variables. So R will be a function of R will be a function of, let's say, another function F1, function of the other variables, that is E, then rho, and T. See, important thing is here R is now the dependent variable, and E, energy E, mass density rho, and time T, they are the independent variables. Okay, in this format, when you express the mathematical relationship like this, let us say equation number 1. Okay, and here we are going to use the Buckingham's phi theorem. And before that, let us write down the dimensions. Okay, so here the variables involved, variables and dimensions. See, the variable R, that is in fact the distance. Okay, so R has the dimension, obviously, since it is distance, it is L. Then mass density rho, and its dimension will be, what is its unit? It is kilogram per meter cube. So therefore mass by cube of the distance, so m divided by L cube. So it is ml raised to minus 3. And then time, obviously the dimension is T, capital, let's say capital T. Okay, and then energy, the energy, what is its unit? Its unit is Newton meter. Newton meter. So when you talk about force, or it is energy and the dimension of energy and work done, they are the same. So force into distance. So what you can do is, force is having unit ml t raised to minus 2, ml t raised to minus 2. So this is the dimension of force. F is equal to m into a. Mass as m, dimension m, and lt raised to minus 2, that is the dimension of acceleration. So mlt raised to minus 2, that is the dimension of force. But here we have energy. So energy, what do we do? That is the force multiplied by the distance. That's work done. So energy and work done has the same dimension. So into L. So therefore this will become ml square t raised to minus 2. So in other words, energy has the dimension ml square t raised to minus 2. Okay. Now you tell me the number of variables in this problem, dependent and independent together. So n is equal to, dependent is R, that is 1 only, 1, and independent E, rho, and T, 3. So 1 plus 3. So total it is 4. And what about number of fundamental dimensions used? Number of fundamental dimensions, that is M. So whether you are using M, L, T, how many of these MLT theta temperature are used? So here MLT only. MLT only. See, look at the dimensions of the variables, the 4 variables involved, R, rho, T, and E. So that involves only MLT. So therefore, number of fundamental dimensions used, that is only 3. Now, as per the Buckingham's phi theorem, number of pi terms, number of dimensionless groups or non-dimensional parameters, number of dimensionless groups, or what do you call pi terms. So that is equal to n minus m. Remember, n is the total number of variables involved in the problem. Here it is 4. Then minus that minus m. M is the number of fundamental dimensions used. Here it is 3. So it is 4 minus 3. So it's only 1. Okay. So therefore, here the important point is the number of pi terms here is 1 only. So here we have, say, pi 1. Okay, 1. So we need to find out only 1. That's why I said it's a very simple problem. So here we have number of items just 1. Number of repeating variables in the pi term. Pi term is formulated by using the variables given, out of which some variables will be repeating. So number of repeating variables. So number of repeating variables is actually same as the number of fundamental dimensions used. That is m. And in this case, it is 3. Okay. And then a non-repeating variable is 1. Non-repeating. Total number of variables in a pi term is m plus 1. So non-repeating variable will be 1. The total m plus 1. That will be the total number of variables in a pi term. Here we have a pi term. I mean, we just have one pi term only. So now total number of repeating variables is 3 and number of non-repeating variable is 1. So total number of variables here is only 4. So therefore, the basic idea is E, R, rho and T here, out of which R, the distance of propagation, see R is the dependent variable. So that cannot be chosen as a repeating variable. So that will be the non-repeating one. Therefore, the other 3, E, rho and T, they must be the repeating variables, no other option. So it is a problem where, we have no difficulty at all to find the repeating variables, to identify the repeating variables, because all the 3 must come there. So repeating variables here, so that will be E, rho and T. Okay, no option, no other option. Okay. So therefore, E, rho and T. Non-repeating variable is 1, and that we will choose as the dependent. So we'll choose R as the non-repeating variable because that is dependent. Okay. Now, how do we formulate now? Formulate the pi term. The next is pi term pi 1. Only one pi term. Pi 1 is equal to. How do we find out? The repeating variables E, then rho and T. Okay. And non-repeating is R. So E raised to the repeating variables raised to the numerical indices. So what is that? So we say A1, B1, C1. The first pi term. So here we have only one, and non-repeating variable without any index. So E raised to A1, rho raised to B1, T raised to C1 into R. So that is the pi term here. So this is the pi term. See, what you should keep in mind is this is the pi term we are going to use. Okay, and we have to find out A1, B1, C1, the index, and then we formulate the pi term completely. Okay, then the problem will be over. And for that purpose, we will insert the dimensions and use the principle of homogeneity to find out the numerical value of the indices A1, B1, and C1. So this is the equation. Let us use equation number 2. Okay, great. Now we will proceed further. And earlier we have the equation 1, that is the functional relationship, and now the pi term is this one. Now inserting dimensions. Our effort is to find out A1, B1, and C1. So what is the dimension of pi 1? Pi 1, it is dimensionless. So it is m raised to 0, L raised to 0, and T raised to 0. And what is the dimension of E? We have written that already. Energy has the dimension m L square t raised to minus 2. And this raised to a1. So this raised to the index a1. And then row, the density has the dimension ml raised to minus 3. And that raised to b1. And then time t has the dimension capital T raised to c1. And then the dependent variable r has the dimension l. Okay, l raised to 1 in fact. Now equating the powers of mlt. In order to find out the indices a1, b1 and c1, we have to equate the powers of m, l and t. Equating the powers of m, l and t. Okay. So equating the powers of m, what do you get? So you are equating the powers of m. See, on the left hand side it is 0, obviously pi 1. Functional group pi 1, has no dimension at all. Then on the right hand side, now m raised to a1 is there. M raised to b1 is also there in this group. And that's all. So m raised to a1 into m raised to b1. So therefore, on the right hand side, we have the powers m raised to a1 and m raised to b1. So the indices can be added. So a1 plus b1. A1 plus b1, and that is equal to 0. So what do we get from this? b1 is equal to minus a1. Okay. So this is the relation between b1 and a1, not the numerical value, but the relation between b1 and a1 we will get. Now equating the powers of t. So what do we get? Left hand side it is 0 and right hand side t raised to 0, right hand side t raised to minus 2a1. See the first group, t raised to minus 2a1 and here t raised to c1. So what you can write? So it will be minus 2a1 then plus c1 is equal to left hand side t raised to 0 only. So that is 0. So what do you get? c1 is equal to 2a1. Or a1 is equal to c1 by 2. Okay. So that is the second one. Here also we didn't get any numerical value. Now we try for the third one. L, equating the powers of L. So what do you get? Equating the powers of L. Left hand side it is L raised to 0. Right hand side it is here. See, L raised to 2a1, L raised to minus 3 whole raised to b1. So that means L raised to minus 3 b1 and into L. Into L means L raised to 1. So the indices should be added up, So left hand side it is 0 and right hand side L raised to a1. So that is simply you write the indices only. So L raised to 2a1, right hand side L raised to 2a1. So 2a1 and then L raised to minus 3b1. So 2a1 minus 3b1 then plus L raised into L raised to 1. So that means plus 1. The indices should be added up. Right hand side when you add up the indices of L, the powers of L, then you will get 2a1 minus 3b1 plus 1 that is equal to left hand side L raised to 0. So the index is 0. Okay. So equating the powers of L, you will get this equation. So as a result, what you can do is here 2a1 minus 3b1 plus 1 is equal to 0. We have already got b1 is equal to minus a1. So that is 2a1 minus 3b1. Minus 3b1. See, instead of b1, now you can substitute minus a1. So minus 3 into minus a1. So it will become plus 3a1. Okay. Then that is equal to this plus 1 can be taken to the other side. It will become minus 1. So what do you get? 2a1 plus 3a1. Like terms can be added up. 5a1 is equal to minus 1. Okay. And from this you will get a1 is equal to the index a1 has the numerical value minus 1 by 5. Okay. And now what about b1 then? If you get the numerical value of a1 as minus 1 by 5, then b1 is equal to minus a1. So therefore the value of b1 will be negative of minus 1 by 5. So it will become plus 1 by 5. So B1 is equal to 1 by 5 there. Then what about C1? C1 is equal to 2A1. So 2 times A1. A1 is minus 1 by 5. So it is minus 2 by 5. So it's very simple. The three indices can be found out from the first pi term. So now it's only, the only part remaining is we have to formulate the term completely. So pi1, substitute these indices. Pi1 is equal to e raised to a1, then rho raised to b1, t raised to c1 into r. Okay, this is from equation number 2. See pi1 e raised to a1, rho raised to b1, t raised to c1 into r. So now we are going to substitute. So substitute the indices. E raised to a1. A1 is minus 1 by 5. And rho raised to b1. B1 is plus 1 by 5. And t raised to c1. So t raised to c1 is minus 2 by 5. Then into r. Okay. So the terms with the negative indices can be brought to the denominator. So in that case, what you can get is maintain rho raised to 1 by 5 in the numerator. And in the denominator, we will be having e raised to, when e raised to minus 1 by 5 is taken to the denominator, it will become e raised to plus 1 by 5. Into t raised to minus 2 by 5, when it is taken to the denominator, it will become t raised to plus 2 by 5. Then into r. And now again, see this 1 by 5 index can be written as common index for the three parameters, rho, three variables, rho, e, and t. Okay, so in what way we will write? So that will be rho divided by e raised to 1 by 5 is there. So rho divided by e into c t raised to 2 by 5. So it can be written as t squared whole raised to 1 by 5. C t raised to 2 by 5 can be written as t raised to 2 whole raised to 1 by 5. So what you can do is rho divided by e t square the whole raised to, see this quantity raised to 1 by 5. Then into r. So only we have to do such algebraic manipulations. So this is the term. This is the first pi term, pi1. Okay. So what we will do next? See, this is pi1, and let this be equation number 3. Okay. See, if you have a problem with only one pi term, then that means the complete problem can be modeled like what? A function of, let's say, let me write another function, say f. Here we have written f1 and f2, I think. See, okay, f and the function of e r rho t is equal to 0, or this distance of propagation r is another function f1 of e rho and t, that is equation number 1. Now we are going to replace the functional relationship of the variable from the, using the functional relationship of the dimensionless terms. So function of another function, let's say f2, function of only one pi term is involved. So pi1, that is equal to 0. See, very important thing is the complete problem can be modeled like the function of pi1 is equal to 0. Had there been two pi terms, then we would have written function of pi1 comma pi2 is equal to 0. So here we have only one. Okay, so this is important. And now, so what do we do next? See, this is, let's say this is equation number 4. See, function of pi1 is equal to 0 means what? Pi1 will be a constant. Very important. A constant, say C. Constant, so let me put say C, capital letter C. See, that is important. So here we have function of pi1 is equal to 0. So therefore, this is the consequence. See, once you have this, what you can write? Pi1 is equal to a constant. So what is pi1? Pi1 is equal to rho by e t square whole raised to 1 by 5 into r. Okay. So just substitute for pi1 now. So what do you get? Rho divided by e t square divided rho divided by E t square whole raised to 1 by 5 into R is equal to constant, say C. Okay. See, the final answer then will be the R is the distance of propagation of the shock wave. So this R is equal to take the other variables to the right hand side, other term to the right hand side. So what you get is R is equal to this constant C multiplied by this ET square will go to the numerator, then divided by the density term rho will go to the denominator, and this raised to 1 by 5. Okay, that's all. So R is equal to C into ET square by rho whole raised to 1 by 5. C raised to 1 by 5 is not applicable to C. Even otherwise, you can write C raised to 1 by 5 is another constant. That's all. So this is the functional relationship for the given problem. So the distance of propagation of the shock wave. So what you can do is, this is that expression for you. Okay.